Um, so the idea, what we've been doing recently, right? We've been talking about synthesis of sound, creating sounds. Yikes. And first we talked about analog synthesis, which was the idea of taking basically an oscillator to create some harmonics and then trying to make some time-varying harmonic spectrum by filtering those things dynamically, change their amplitude, and then running a dynamic filter to move those things at the same time as changing the pitch underneath or controlling the pitch underneath. And that was a good way of making some sounds which sounded interesting and were useful for music, even if they were obviously synthetic. And then last week we said, well, look, let's look at, these things don't sound very real, so let's look at some real sounds. If we look at the spectrogram, which is just one way of looking at it, but seems to be quite a revealing way of looking at a sound. We see these harmonic tracks, and then it's like we can just extract the parameters from those. We can then run a lot of sine wave oscillators, and we end up with something which sounds a lot like the original sound. We can make some very realistic simulations of real sounds. And we've still got the opportunity to control it, that we can then take those individual sinusoids and we can change their amplitudes and their frequencies, modify the sound in a kind of predictable way. But there are a couple of problems with sinusoidal models. Firstly, they're very expensive. That to get a good quality synthesis of a sound with a pitch of 100 hertz or something. Maybe you want to go up to 8 kilohertz, so you need 80 or something individual oscillators, which is just a lot of calculations of sine. And by the same token, they need a lot of parameters, right? If we're going to have new frequencies and magnitudes for every one of those sinusoids, 80 sinusoids maybe every 10 or 20 milliseconds, we're talking about a lot of numbers. And of course, we said, well, the frequencies probably aren't independent. We probably want them all to be multiples of a common fundamental. But in general, you might want to have sounds which are not harmonic or whatever. So they're fairly expensive models. And so today, LPC actually is what they were doing with digital synthesis at the time of analog synthesizers. It's cheap enough that you can run it even on 1970s technology. So there's this toy called Speak and Spell. How many people know what that is? That's amazing. Speak and Spell is a very kind of iconic 1970s toy. It's just this little plastic thing. It's meant to teach toddlers how to read or something. But you press. It has a little, fluorescent display, and it selects a word, and then it has a keyboard, and you have to spell out the word. But it speaks the word to you, and then you have to spell out the word, and you have to get it right. So it has to have speech synthesis in it. And the question was, well, how do we create a toy that we can sell, a few tens of dollars, using 1970s technology that can do speech synthesis? Now today, you just record it and have it, burned into a chip, but that would be very easy. But at that time, even putting a few kilobytes of memory into this device is very hard. So there was no question of sampling audio. I'm trying to think. Because that approach of putting a sampled sound into a device wasn't feasible for 10 or 15 years after that. But at the same time, so we can maybe store it more efficiently as a parametric thing, but then we have to have the computation to resynthesize from the parameters, and we don't have very much computation. But the solution was LPC, that they stored it as a phonetic representation, but then each phoneme was represented by an LPC system, and it was something that TI could build in the 1970s and sell for reasonable prices, and it was a very successful device. So what is the technique? The technique basically, as Binyan said, is to have poles, a resonant filter, and we know that's a very cheap and simple thing to build. Now, why is it that resonant filters are so effective? I've thought about this a fair amount because it keeps coming up. I actually wrote a book chapter for a handbook on phonetics. It was like a reference book for linguistics students who wanted to learn about phonetics. And I was trying to sort of, if you didn't know anything about electrical engineering, how would you understand the idea of an all-pole filter? And it's all about resonance. And resonance is actually a very intuitive thing for us, because that's what happens with a child's swing. That basically, this is just a pendulum, right? But you have some kind of mass on a string, and it wants to oscillate backwards and forwards. And this is something that we've all done, so we know what it feels like. And this is nice because it's sort of, there's this in an oscillator like this, in a resonant, this is a simple harmonic motion, second order differential equation. But the point is you've got two components. You've got the position, which is the thing you can think about plotting, and you've got the velocity, right, which is the derivative of position, but has this thing that it's out of phase, right? So when you're in the middle, when you're in sort of central position here, you're going at the highest velocity. And then when you're at the actual extremes, your velocity goes momentarily to zero because you're stationary. And that's kind of like any simple harmonic motion system has to have two places to put the energy. So in this case, it's the gravitational potential energy and then the kinetic energy of the motion. And in in a spring and mass system, it's the potential energy in the spring. And then in electrical oscillators, it can be the current and the voltage, or the charge and the flux if you've got an LC circuit or something like that. So they're very easy to set up. And we, if you think about swinging something, you have this idea that if you have a pendulum, you try and swing it too fast, you can make it move, but it's only when you hit resonance you get these really large amplitudes. And so that gives you a nice feeling of the sense of a bandpass filter that has a best frequency. So it turns out that the vocal tract is also something we can model as having these particular resonances. And in fact, the way that our speech communication system works is by having an oscillator at the vocal folds and having a bunch of resonances which can be moved around in real time by moving the tongue mainly to shape the speech. But these resonances are simply just poles, which means that we can build them with these filters, IIR filters, all pole filters that we know about and that we can handle very easily. So here's the kind of the DSP view of resonance, which is a system like this, a feedback filter. Right, takes the input, takes the output, and has two delay elements with different gains feeding back. This gives us our second order IIR filter, which is going to have, assuming these coefficients are real, we'll have two conjugate complex poles, which give rise to a frequency response like this. So there'll be a best frequency where the gain is large. And the gain here is, if I put in a sinusoid at a certain frequency, what do I get at the output? Right? And so here, if I put in a sinusoid I didn't label the axis here, but this should be unity. So if I put in a sinusoid here, it gets 8 times the amplitude out. Depends on the coefficients. If I put it in lower than that, it goes down to 0. And I guess it depends on the coefficients. It goes down to some constant value at 0 hertz. And then at a higher frequency, it dies away and eventually disappears altogether. The angle here, so this is the projection of this is the pole zero diagram, if you remember that. The angle here is the frequency. So as this angle gets larger for these poles, then the resonant frequency gets higher and higher. And the radius here, how close it is to the unit circle, controls the resonant peak here, which also controls the bandwidth of this peak in the frequency response. So if we put an impulse, a click, into a system like this, we get this impulse response, which is a classic resonant impulse response. It's got the resonant frequency here, coming from the angle of these pole pairs, and it's got an overall decay here, which depends on how large this radius is, how close it is to the unit circle. If it's on the unit circle, it'll be metastable, so it'll keep oscillating forever at that one frequency. But as long as it's inside the unit circle, it'll decay away. But if it's just a little bit inside, it'll take a long time to decay away. But this is also, this is what happens with the swing or the pendulum. You knock it, and it'll swing backwards and forwards, and eventually it'll die away. It's also what happens, with a drum head. If you, well, I don't know, some kind of, a tuning fork anyway. If you knock it, you get something like that, just at a higher frequency. And then, but the interest, so this part, this is very physical and intuitive. This is a little bit surprising, that to build it out of in a discrete time system, we just need two steps of memory and a couple of multiplies. So this oscillator, this one has a period of what, like 20 samples or something. But to get that 20 sample period oscillation, you don't need 20 samples of memory. You just need 2 samples of memory. You can make it if you make this theta very, very small, you can make this have a very, very low frequency of oscillation. But all it's thinking about is the last 2 samples. You can't do it with 1 sample, but you can do it with 2 samples. And the gains are also kind of, so what are these numbers here? Well, this one is just r squared, which is, as r gets closer to 1, this thing gets closer to sustain. So here we have a 2-sample delay where we're subtracting back almost the whole thing, just a little bit less than the pure signal. So this one doesn't control the frequency. The only way the frequency comes in here is with this one, with the 1-sample delay, which has the cosine of the frequency in here, and also scaled by 2r. And so cosine starts off at 1 and goes down to -1. Right? So here it's 1, and then for all these frequencies down here, it's to -1. So if you have, something just a tiny bit less than 2r here and minus r squared here, then you get this very slow oscillator. But as this number gets smaller and goes negative, then the oscillations get higher. So it's not, it's kind of a surprising fact to me. That's all you need. But what that's saying is that, this is a recurrence relation to generate this sinusoid, which is kind of a nice thing. Okay, but that's why these things are cheap, because we only need 2 delays and a couple of multiplies to build a single resonance. It's a bandpass resonance like this. And then, of course, we can add several of these to get multiple resonances, which is what we need for a good model of the human voice. So what's going on in human voice? This is a spectrogram of one of these sound examples. The football coach had a watch thin as a dime, one of these timid examples. And it's plotted in such a way that you can sort of see, this is actually a wideband spectrogram. So now we're not seeing the harmonics. Instead, we see these vertical structures which come from the individual pitch pulses. And the reason we're doing that is because we're not interested in the frequency detail and level of the individual harmonics. We're looking for these broader scale features which come from the resonances of the vocal tract, because basically there's some buzzing going on with the vocal folds, but then it's being shaped by the vocal tract. And this is International Phonetic Alphabet. This is the convention for labeling the different phonemes here. Sometimes you can see it's, so the model underlying that is when people speak, they make a particular sound for a little while, then they switch to a different sound. And that particular sound is defined by these, you see these stripes, these are the resonances of the voice, the formants, as Binion said. And here, so this is thin as, to make an N, you open a flap behind your nose or something. So it's very it's pretty much an instantaneous thing. So you see there's a sudden change here. So there, to say that N is 2 different sounds with different spectra is pretty reasonable. But here you see some of these are not quite so clear. So this is a watch. And W is not a fixed spectrum. It's called a glide. It's a change. And so it's this motion, which is W. It's like you're moving your lips back and doing something with your tongue. And what's happening is all these resonances, when you're going woo, you get this low frequency, and actually there's a high frequency up here which you can't see. But when you open up your lips, those resonances sort of move back in, and that's the classic sound of w. And so even though the phonemes aren't, this is kind of a fiction, that they're these successive chunks you're putting together, the formants are a pretty good model of what's going on. The idea that basically what's going on with speech, well, you're gating the energy, but then you're moving these resonances around, and that just moving these resonances around will give you speech. That turns out to be pretty successful, and that's why you can build these good LPC speech synthesizers. And we only need like 1, 2, 3, 4 of these resonances, right? So we had, on the previous slide, we had 1 resonance, 2 poles. And you can get good speech, you can get intelligible speech with 3 resonances, 4 resonances, 8 poles, an 8th order IR filter. You're doing pretty well. And all you need is to be able to have this filter move with time, right? You need time varying control of the poles, but then you're pretty much done. So this is this leads to the source filter model, which was originally a model for speech coding, so trying to take the speech signal and then reduce it to a lower data rate to make it as effective as possible. But then there's also a model for speech synthesis, for generating speech from parametric descriptions. And I guess it's kind of it's also a phonetics model. It's like a way of understanding how the speech signal works. And so the idea is you have 2 components in speech. You have the source, which is it's like the oscillators in the analog synthesizer. It's the fine structure, it's the actual detail. And in speech, this comes either from this sort of approximate impulse train coming from the oscillations of the vocal folds, or in sounds like sh, it's a turbulent noise coming from some constriction in the vocal tract, which is basically, you can treat as like white noise. So you have this periodic or aperiodic excitation as the source, then you put it through this filter, which is just a set of resonances in the vocal tract, a set of poles whose frequencies are called the formants, and those things move around in time. That's it. And then there's some coupling between the mouth and the atmosphere, which basically is a fixed, I want to say low-pass filter, but it's got some fixed filter characteristics, not very important. And that gives us speech. So now we're saying, well, if we can just parameterize each of these components, we can represent the entire signal. To represent this, we need to know basically the frequency, the period of this glottal pulse train. They're not exactly impulses, but they're impulses with some fixed spectral shape. So either the frequency of that, or the fact that it's not any frequency, it's just white noise. And then that you have to update those frequently, every 50 or 100 times a second, something like that. And then the frequencies of these resonances, and again you have to update those frequently. But the rate at which these can change is limited by how quickly you can move your tongue around. So it's like there's a physical mass that has to be moved by muscles. It doesn't move that quickly. Maybe the thing like the nasal flap can change pretty fast, but the actual formants themselves can't change too fast because you have to actually move your tongue. And then, you have to figure out how fast you have to update these to make the speech sound reasonable. And it turns out that 50 to 100 times a second is enough, is plenty. So now we've got to set, but now this is like maybe 4 or 8 parameters here, 4 frequencies and maybe 4 gains. And then maybe, turns out you need maybe 6, 7 bits to describe the pitch adequately. So maybe 7 or 8 bits. So, and then the whole thing 100 times a second. We're down into the thousands of bits per second or less, which is a lot better than, 64 kilobits that you need to directly encode the waveform. So this becomes a very efficient representation. It gives pretty reasonable quality synthesis, as we'll hear in a second. And we've still got this nice situation where the parameters are somewhat meaningful. That if we want to, we've got an actual pitch track in here, so we can change the pitch of the voice just by scaling these parameters. We've got a set of formants in here which, with a little bit of manipulation, we can express as a set of frequencies. And so we can do the stuff that Binyam was showing of actually just warping all the frequencies in a kind of consistent fashion. And it works because it sounds like you're actually changing the shape of the vocal tract, changing the length, the physical size of the speaker. And you can do those independently. Okay, so that's the source filter model, the motivation behind this. How do we actually do this mathematically? And this is the equations you've already seen. The reason it's called LPC, linear predictive coding, is this idea of, for coding, for reducing the data rate, you need to transmit a signal. And there are lots of perspectives on this. One of them is this sort of information theoretic perspective, that if you have a signal that's got a spectrum that is not flat, that means that there's it's not a white signal, the successive samples are not statistically independent, which is the same as saying there's some statistical dependence between successive signals, which means there's some redundancy. If I give you a set of samples, then you know something about what the next sample is going to be, which, in information theoretic terms means that if I then tell you exactly what it is, without using that information, I've wasted some information. And so by the idea of linear predictive coding is you can try and make the best linear prediction of the next sample, and then all you need to encode is the difference between that what the prediction would be and the next sample. And that's kind of like that's the part that you cannot predict. That's the non-redundant, the innovation in the signal. And as a coding scheme, you want to be able to do that at both ends. So the only information you're transmitting is the reconstructed signal. So the prediction is based on the signal so far, but you try and find a set of parameters here that will give you the most accurate prediction of the next data point based on the previous data points. And then you have some finite order here, which is how many of the preceding data points you allow yourself to look at. But basically, the idea would then be, at the transmitter end, you're solving this expression. You're finding these AKs, which allow you to not different for every point, but for some block of points, are going to give you the best prediction. You then just transmit the AKs, and at the far end, they also have, they're also reconstructing this thing point by point, so they can run the signal. And then maybe transmit these error points. If you want perfect reconstruction, you can transmit these errors, but the errors will be much smaller. The differences will be small, and so you need a fewer bits to encode them or whatever. And so it becomes a more efficient coding scheme. So these are the AKs, are the linear predictor coefficients, which would be sent once every block or maybe once for a whole signal. And E of n is the residual, the difference between what the fixed predictor gives you and what the actual original signal really was. So that perspective makes the name linear prediction seem very natural, because that's exactly what we're doing. But as Binyan showed, when we actually analyze this, if we take the z transform of this whole thing, we then get, S of z is, z transform is linear, so it's sum of ak s of z times z to the minus k, because that's what happens in z transform, plus e of z. And then we can bring all the s of z's onto one side, and we end up with this transfer function, which is just this, in the z transform, is just this single finite order polynomial in z, which is saying that the output s of z can be generated from the input e of z by passing it through this filter, whose z transform is 1 over a of z, where a of z is the finite order polynomial in z, which is to say this is just an all-pole filter with a finite number of poles. The number of poles is the order of the linear predictor here. So this thing is called, these all-pole IIR models are also called autoregressive models. Regression is the idea of trying to predict a signal from something else. If you try and predict it from itself, it's autoregression. So these things are also called AR models. That's what they're called in statistics, basically. So that's the model. The only question is how you find these AK parameters. Of course, it doesn't matter what you do. If you're including this as well, then you can make it work. But the idea is to try and get these AKs to minimize the amount of information you have to send here. And the natural thing to do there is to, wait, I'm not going to tell you that yet. The natural thing to do there is to minimize the energy of this. But I'll show you that in a second. Okay, what's coming here? All right. So the idea that in the AR model, it's just you're taking the input excitation, putting it through this filter to get the output. That, of course, is just the source filter model, right? That's exactly what we had. That we have some input, which is now we're going to call En, the error or the innovation. And then we have the filter, the vocal tract filter, which we're now going to just have as this 1 over A of Z, because it turns out that actually the vocal tract, if you model it as a series of tubes of different cross-section, you can show that that system, which is basically a set of waveguides, transmission lines with different reflection coupling, right? So it all works out very nicely in that waveguide analysis. That is exactly this, a system with just poles. Not particularly obvious why that should be, but that's how it works out. That the waveguide, which is basically delays and then reflections with different gains, the net result is a set of poles. So this is to get zeros, you need like energy dividing, and so actually when you let some of the energy come through your nose, then the system becomes a system with zeros. But if you don't worry too much about nasals, which is the majority of speech sounds, it's just a single tube, and then you can model it very accurately with a set of poles. So that is our basically, almost if you wanted to come up with the best signal processing model of the vocal tract, this is kind of what you'd end up with, and it just happens to be the same as this kind of nice information theoretic model of how to predict a signal. And then we've got this idea that, okay, well, this only this model of the vocal tract in terms of these poles is only valid for a single configuration of the vocal tract, but it doesn't move that quickly just because of the mechanical limitations. So if we say that it's piecewise constant over 10 to 20 milliseconds, 50 to 100 times a second, we're okay. Unless we have nasals, in which case suddenly the best model would have zeros in it. But you can always find the best all-pole model that approximates this thing that wants to have zeros. It's not as efficient. So how do we find the parameters? That's what I was. That's the obvious question. If we actually look, if we looked at the spectrogram, we saw those dark bands, which were the resonances. And if you look at a single slice through a spectrogram, or a single DFT of a little window of speech, you might see something like this. And so these things are the individual harmonics of the pitch. This is like maybe over a 30 millisecond window. They can get kind of hard to see. You can see them again up here, but in here they're kind of a little bit messy. Depends on the noise and the window alignment and stuff like this. But you can see, so there's fine structure here coming from the harmonics of the speech. But then you can see these underlying peaks, and they're very clear like this. This is on a log scale, right? So this is like a 60 dB range. But these things are these very nice, well-defined peaks, and those really are the resonances. That's why, that's the evidence that this is a good model, that speech does tend to have these fairly broad, well-separated resonances, which are going to be able to, which we're going to fit pretty well with an IIR filter. Mathematically, the way we do it is by saying, well, let's find the AKs that minimize the energy of the residual part, the excitation part. And so if we just if we put the E, we had S of n is equal to the sum of AK S of n minus K plus E of n. So you put all the S of n's on one side, put the ENs on the other side, square both sides. We now have this equation for the sum of En squared, right? Sum it all over some window. And then we can say, well, what are the AKs? These are the unknown parameters. What are the AKs that are going to minimize this total energy? It turns out to be very simple. You just differentiate with respect to each of the AKs, and you get an expression for. You get basically a nice n by n matrix expression, and it turns out that the parameters in that expression are just these things, the autocorrelations of the signal itself. You could do this very easily. Of course, you have to verify this is a convex expression, but it is. I think it's pretty clear that if you're summing something in energy here, then it's going to be a nice convex thing. There's going to be some minimum here, and so it turns out to be a very simple expression. Of course, in Speak and Spell, they didn't have the analysis running in real time. The analysis was all done ahead of time, and so these AKs were the only things that were encoded. But it turns out that even this analysis for LPC, it's, involves solving a set of P simultaneous linear equations, but it's not that bad. It's just inverting a P by P matrix. Or, in fact, there are even simpler ways because the P by P matrix is very highly structured. So there's a pretty simple recursive expression which will do it in P steps or something like that. And it just depends on calculating the autocorrelation across your signal. So you just have to take your chunk of samples, however many samples you want to encode, calculate their autocorrelation out to P steps, however many, whatever order you want. And that gives you the P coefficients, and then you put them into a matrix and solve it. So here is an illustration of what the kind of things you get out. And so now what this is doing is it's doing the LPC analysis on a single frame of speech. So this is, what is this? This is like 500 samples here. Maybe 512 samples. So that's probably 32 milliseconds at 16 kilohertz. Something like that. That's the kind of time window that we want. And then it's been hand windowed. It's been, it had some tapered window on it just to remove the artifacts at the edge. I always do that because in general, particularly if you're going to take like a spectrogram or something, you want to get rid of those discontinuities at the edge. For the purposes of LPC, it's not clear whether that's the best thing to do or not, because if you're just calculating the autocorrelation, maybe the edge takes care of itself. But anyway, that's what we've done here. But you can see that basically it's the speech with the blue line is the original speech, and you can see the original pitch pulses. They've been sort of attenuated at the edge, but there would have been pitch pulses every 10 milliseconds or so in the original. Okay, so that's the original speech. And then here's the spectrum. So the blue line is the spectrum of that blue signal up there. And then we do the LPC analysis on that signal to find, in this case, a 12th order model. We solve for the 12 AK parameters to give us a 12-pole model, which is 6 pole pairs. And here they are on the Z-plane. They're all inside the unit circle. You can, if you, depending on exactly how you do the autocorrelation, you can guarantee that you end up with a stable system. So you can guarantee that all poles are going to be inside the unit circle. And this filter defined here is its spectrum on this same plot is this smooth curve here. And it's exactly what you'd expect. So it looks like a smooth approximation to the blue curve, but it also looks like the output of a filter with basically 3 or 4 resonances here. Now, it turns out that to find the best solution, the math put together a pair of poles here, so this is actually the result of 2 poles, and then you can sort of see there are 2 nearby poles here, which are these 2 here, and then a couple of peaks up here, which are shallower to just keep it flat and mirror the poles up there. But with only 6 poles in the positive frequency half, the frequency response has got to look pretty smooth. It can't be anything nearly as jagged as this. There isn't enough information. And so if you're saying, well, it's the optimal solution, right? We solve this nice squared error expression. So this is the best possible approximation to the blue curve under the metric that's using. The metric that's using is the magnitude of the error in the time domain, the magnitude of the squared error, the energy of the error in the time domain, which, according to Parsifal's relation, is also the squared error. It's the smallest squared error in the frequency domain. But this is not actually showing the spectrum in linear units, it's showing the spectrum in log units, which means that a difference here, which is a fixed proportion, like this is a 5% difference up here, it's still a 5% difference down here. But 5% of this is like, 30 times larger than 5% of this, because this signal is 30 times larger than this one, something like that. So what happens with this approximation is it fits very close during the largest parts in the spectrum, and it's much less of a close fit in the valleys in the spectrum, because the amplitudes here are so much smaller that it would much rather use the modeling, whatever degrees of freedom it has to get to reduce the error in these peaks. And so this is a classic feature of these LPC models, that they fit the peaks very well and they're kind of very smooth and don't worry about the details in the valleys. And that also seems to work very well perceptually, that when people listen to these signals, they're much more interested in the inaccuracy and the details in the peaks than in the valleys. And so that's one of the kind of nice sort of side effects that comes out. Okay, so what are these red lines here? Well, if I have a filter like this, if I took a signal and put it through an all-pole filter, it would, if it was like started off as a noise signal, a flat noise signal, I'd end up with noise shaped like this. But I might want to say, well, I'd like to recover the actual original signal from that. I'd like to get the inverse. I'd like to inverse filter this thing to recover the original signal. This filter, which is got all poles, and all poles are inside the unit circle, it's a minimum phase filter. That means I can build the exact inverse of this simply by replacing all of these poles with zeros. If I have another filter, which is now a pth order all zero filter, FIR filter, then if I put a signal through this filter and then through the all zero equivalent, each of these poles will be exactly eliminated by pole zero cancellation. And it would be the filter whose frequency response was the mirror image of this. Sort of this thing would have the largest valley here, and then it would have the biggest peaks up here. But also the phase response would be exactly complementary as well. So you can exactly undo the effect of this kind of filter by taking the all zero version, which is actually just taking the AKs and treating them as parameters for an FIR filter rather than an IR filter, treating them as the impulse response of a filter. And so you can take the original signal, put it through that inverse filter, which is the same parameters, just treating them as FIR, and you get this red signal here, which is the flattened version of the original signal. The red signal is actually exactly the difference between the blue signal and the gray signal. Because if I take the red signal and filter it with the gray frequency response, I get the blue signal back, right? So to get the red signal, I took the blue signal and filtered it with the negative of the gray response. And so it's basically subtracting that off. So that's why it sort of looks flat here. It's the amount of error between, it's the difference between these two things. So you see here, this big peak in the red signal is from this sort of little area here, where the blue signal is mostly above the gray line. And down here, these valleys in the red signal are these chunks down here where the blue signal is significantly below the gray line. So the red signal in the spectrum domain is just the original signal minus the smoothed approximation to it. But this red signal is actually in the time domain. I'm taking this blue signal passing through as FAR filter. So this is what it looks like in the time domain. And it's basically this red signal, the blue signal, but without any of the kind of the low frequency stuff. It's like you've boosted up all the lower frequencies. You can only boost them in this fairly smooth way, and it has to be fixed filter. But as far as possible, it's turned this into a flat spectrum, a signal with equal energy in all frequency bands. And so it's called the whitened signal. Okay, so let me play you some examples now. If you go to the website for the class, you'll see some MATLAB commands to generate these kinds of plots, to do this for a single frame. But of course, if you do it for a single frame, it's not that, I can play you 30 milliseconds of speech and then play you the same thing flattened. It's kind of too short to hear what's going on. Instead, what we do, of course, is we chop the speech up into successive 30 millisecond frames and then estimate the LPC for each one of those, and then we can model the whole signal. And so I have a function to do this, LPC fit, if we actually look at that, it takes the input signal and the order of the model, number of poles that you want. But just does some stuff up here, but basically chooses the number of hops, pulls out some segment of that signal around that hop. So it just takes x from hop minus the hop number times the hop size plus 1 to the window length, applies the Hamming window, calculates the autocorrelation, right, which is the coefficients we needed. Just these p autocorrelation coefficients. And then basically it sets up this matrix, which is a Toeplitz matrix, so it's the same row shifted down, and then just takes does the least squares solution to that, which is the inverse of that times one row, and that gives us the coefficients that we need. That's basically all it is, does that for every frame. So that gives us a matrix here, A, which is 13 coefficients for a 12th order filter. So if I look at A1 here, it's basically a set of 13 filters, and the 13 coefficients. The first one's always 1 because it's a 1 minus AK, zeta minus K kind of thing. It also gives us this G, which is the gain for every frame, so that it's like the overall scaling gain, which you need to control independently. And then it gives you this E, which is the inverse filtered original. So the length of D here, the original speech, is 27,000 points, and then E is a little bit longer. It's rounded out to the nearest frame. So if I play the original speech here, okay.
Cottage cheese with chives is delicious.
I can then take this residual, and we can listen to that. So it sounds kind of like static, which is to say it sounds kind of like white noise, but you can hear the buzz of the original pitch in there, right? So if we plot the original and the residual next to each other, axes, x. Not sure what happened there. Let me see if I zoom in on a part of this. Oh yeah, it's kind of, the scaling's not working so well. This is the residual in the middle here. And you can see during the pitch cycles, you get these very clear impulses once every pitch cycle, which is basically saying, yeah, we can get a pretty good model of this signal by having some kind of set of resonances. The amplitude is smaller here, but you can sort of see these individual pitch cycles. Have these resonances, and then just feed something close to an impulse into them once every cycle. And then the resonances kind of get excited, and they die away. Of course, we don't have. We can do the thing of having the inverse of LPC synth does the converse of LPC fit. You give it the matrix of filters, you give it the gain coefficients, and you give it the excitation signal, and it'll chop up the excitation, that buzzy thing, into little frames, filter them by the corresponding filter, then overlap and add them back. And this thing...
Cottage cheese with chives is delicious.
It sounds pretty much identical to the original. It's not quite identical because there's some overlap add going on, but you have to listen quite carefully without the stupid hum to hear the difference. But if we don't give it an excitation, if we look at what LPC synth does, it's taking the excitation and filtering it, but if you just don't give it anything, it'll just take a white noise sequence of the same length. We could just put in, white noise here instead. So we could just say rand n of one row and whatever it was, 28,000 points. It'll do that automatically by just putting it in as an example. Now,
Cottage cheese with chives is delicious.
Okay, so if we look at the spectrogram of the original, how does that look? Yeah. And the spectrogram of this reconstruction, this signal, which we just heard, is basically just white noise filtered with these successive all-pole filters. But you can see that they've done the thing of picking out all these individual pieces, right? That there was some filter here, it was stationary for whatever, 25 milliseconds or something, so 1/20th of it. It's actually shorter than the columns in the STFT. But enough to sort of, it was modeled on this, so it was saying, well, there's energy here and less energy elsewhere. And it's enough to reshape the white noise to carry these resonant peaks that we're hearing in the speech. Actually, we should use a shorter window here for to see the formats better. Oops. The middle one is now not it, but this is with a short window where you can sort of see the pitch cycles. And here you can see that it's kind of doesn't have any pitch structure, but it's got the same resonances here from the formats. And that's why if we listen to that again, you can actually understand what's being said. I'm gonna pull the display out to stop the buzzing. Okay. This is the original speech. Oh, no, that's the excitation. This is the original speech.
Cottage cheese with chives is delicious.
And this is the noise-excited resynthesis.
Cottage cheese with chives is delicious.
So it's mostly pretty intelligible. It just doesn't sound like that. It sounds a little bit like whispering, but it sounds kind of like this weird kind of hoarse whispering thing. But that's pretty exciting because it's telling us a lot about where the information is, right? It's saying, well, if you just keep these filter coefficients, which are now very little information, 13 values 100 times a second, you actually preserve most of the linguistic information. So that was that. And so speech recognizers basically only use that information. They throw away the excitation, the residual part, and just use the resonances, the formats. Okay. So, any questions about that? Get the point? Yeah.
I'm willing to accept this. Why is minimizing the energy of the error is the optimal result in terms of like the reconstruction of the sound there? It seems very intuitive in communication systems.
Yeah. So why is it minimizing the error? Minimizing the error is kind of, the way it came out, which is minimizing the error of the prediction in the time domain, that seems reasonable, but doesn't seem like what we're trying to do. But minimizing the error of the residual in the time domain is it's the same thing as making this gray line as close as possible to the blue line, right? So it's just because we've shown that model of the feedback is equivalent to a filter. It's not, okay, so it's this gray line plus the gain, right? Because that's the other term, the G term, that we have to move it to make it shift up and down to get the right thing. But we've shown that under that model, which is the set of coefficients feeding back, that is a filter, and that minimizing the residual there is making this filter as close as possible to the spectrum because of the Parseval's relation, that the difference here is going to be the difference here. And so then in that sense, we're not minimizing a residual energy. We're getting the least squares error approximation to the spectrum. And so that makes sense. So that's kind of what we're trying to do. And then because we've constrained the thing that it's optimizing over to be, it's got to do the best fit you can get using 12 poles. So you're constraining the fit to be this space of smooth spectra, which only have up to 6 peaks in them at some point. The peaks could be very sharp, but here the energy is quite spread out, so that it's going to use these broad peaks to cover a bunch of energy, and it's going to try and fit them in this smooth way. So basically, it's a smooth spectrum, which the normal signal processing way to get a smooth spectrum would be to take the detailed spectrum and then just put a low-pass filter through it to sort of smooth it out, like a moving average filter. This is a different kind of smoothing. It's a parametric smoothing where you say, well, I'm going to take this set of parametric filters, which are intrinsically quite smooth, and then find the best one out of that space. But it turns out that's mathematically very easy to do and gives us a nicer result. It turns out. And the reason that it's nicer than just smoothing is, firstly, the filter we get is very easy to implement, and secondly, because it turns out, in terms of speech, the system we're trying to model really was a broadband signal being filtered by a bunch of resonances. So trying to model it as a set of resonances gives us a really good fit a lot of the time.
If you're aiming at the human ear, wouldn't it really make sense to try to get the frequency response or the ear and try to maybe come up with a
Right. That's a good point. So this is what we call source modeling, right? Which is looking at where the signal comes from, looking at the structure of the signal and trying to model that as a way of coding it. Source coding, it's called. But what we're actually interested in, maybe, is a representation that is optimal for the listener, right? For the receiver. And there it's like, well, we got some error in here, and we can show that it's, we've minimized the squared error. But that's only a good thing to do if we know that that's the criteria that the receiver cares about. And we're quite a long way from that, right? We haven't really done that. We haven't. That was no reason to believe that what the listener cares about is the squared error. Clearly, if it goes to very small, it's an upper bound. But the listener is probably sensitive to a bunch of different features that are not that. It turns out, and I don't have a really good answer for this, if you look at the structure of the ear, it has these bandpass filters which are varying in bandwidth. It has this representation which picks up some of the time structure, but definitely sensitive both to pitch and to this format structure. The reason that you can understand that that filtered noise, the reason you can understand that speech at all is kind of surprising. It's sort of like, really? That doesn't seem, you've never heard a person speak like that. Whispering is a little bit like that, but not so much. There are weirder things, right? Which is, we can take, I'm going to finish answering this. We can take these filters, right? Each of these for every frame here, we've got a set of poles which correspond to the spectrum here, but the poles kind of show you where the peaks are in the spectrum. We could actually go through that and do something like the sinusoidal modeling, where we say, okay, well, I'm going to take each of these frequencies and magnitudes and sort of track them through time and use that as some kind of representation. And this is this so-called sine wave speech, which was investigated by Robert Ramez from the psychology department a few years ago. And so it's like these red dots here are these individual peaks. And so they're pictures, they're like little ridges on the spectrogram. But now instead of following the harmonics, they're the ridges on a broadband spectrum, they're following the formants. And so we see that they're not harmonically related. And there are only 4 or 5 of them covering a few kilohertz. You've never heard anyone speak like this. But the amazing thing is that speech is also somewhat intelligible. I don't think I have it running on my machine, but if you go to my web page, then there's this set of examples for this. And I was kind of hoping that we actually had okay. Oh man, I don't have the examples here. I'll play them for you on Wednesday. What you get is a set of whistles, right? Incoherent whistles, but they're sort of they have similar amplitude modulations, but the frequencies are moving in different directions. And when you listen to it, you can hear it as whistles. But then if you somehow get primed to hear it as speech, you can understand the speech. And so what I was going to say is, it appears like at some higher level in the auditory system, we're so optimized for listening to speech, that we do actually have mechanisms in the brain which are looking for these resonances, and they're going to find them wherever they can. And then when they find these resonances, they're going to try and stick them together into speech, because we're so, it's so important for us to understand speech in all possible situations and with the least amount of energy. And so we tend to interpret even things which are not at all like speech as speech. That, incidentally, that's why the wah-wah pedal is an interesting effect, because the wah-wah pedal has this moving resonance, which sort of looks like a speech resonance, and suddenly kind of excites these speech detectors in your brain that sort of, it makes it sound interesting. All right, I've kind of overrun here. We can do this. There's this thing we can do where we rather than just having only the LPC parameters, we can have a very, very crude representation of the excitation where we just say it's either a set of impulses with a certain pitch or white noise. And that, is even better than the pure noise synthesis and sounds pretty good. Maybe I'll play you that, or that's on my website. Here's the warping that Binyam was talking about, that we can just take these frequencies and warp them, and you can do all kinds of interesting modifications.
Cottage cheese with chives is delicious.
So here's that one warped.
Cottage cheese is delicious.
I messed it up, but it sounds like, here, I'll play them again.
Cottage cheese with chives is delicious. Cottage cheese with chives is delicious.
So the pitch is the same, it's the same prosody, it's the same rhythm, but it sounds like he's a little kid now. It sounds like a chipmunk effect, right? Which is strange. And so on Wednesday, we'll look at using some LPC analysis and synthesis in real time in PD, and in particular using it for cross synthesis, where we take the excitation from one signal and the filter from the LPC filter from a different signal, and you can combine the sounds of two different voices. Okay, so that's what we'll look at. Any questions about that? All right, great. I'll see you on Wednesday then.